So, thank you. Welcome back. I've been warned that yesterday's talk went a little fast for many people, so I'm going to try to be a little bit slow. There'll be some material in the slides that I will skip that you can look at the slides afterwards if you're curious about. So when I flash up the pictures, hopefully the pictures will go, oh, I wonder what that is, and you can go chase down the papers. But I'll try to be a little bit slower today, but please do feel free to interrupt me with questions at any time. I'm sorry, I should have said that yesterday. And I should explain that normally when I give talks, I think of these as advertisements, not as I'm presenting the technical details. So if at any point some technical detail is missing, feel free to interrupt and ask. Okay, so the basic question that I want to talk about today is one that dates back to, again, the late 1800s. Given two curves on an orientable surface, are they homotopic? So just to make sure that we're all on the same page, though, I first need to explain what an orientable surface is. I need to explain what it means to be given an orientable surface. I need to explain what it means to be given two curves on an orientable surface. And of course, I need to remind everyone what it means for these things to be homotopic. So let me start by just talking about surfaces. What I generally mean when I say given a surface. From a mathematical standpoint, that means one thing. From an algorithmic standpoint, that means something slightly different. So from the standpoint of mathematics, topologists, when I say surface, I mean a connected, compact Hausdorff space where every point has a neighborhood that locally looks like the plane. There's homeomorphism from the neighborhood to R2. And I'm only going to be considering orientable surfaces, not because the theory doesn't go through, but just because it simplifies and removes a bunch of cases. So an orientable surface is one that doesn't have a subset homeomorphic to a Mobius band. As you probably already know, once I decide that I'm dealing with closed, compact, orientable surfaces, I can classify those surfaces by a single natural number called the genus. So the sphere has genus 0, the torus has genus 1, a pretzel over there has genus 3, and generally, intuitively, although it's a little bit dangerous in some ways to think about this, you can think of a surface of genus G as a sphere with G handles glued on. That's a good way to think about how to construct the surfaces. That's really not a good way to think, here's a surface, what its genus is. But for our purposes, this is good enough for now. Now, when I'm talking about what it means to be given a surface, I'm not just given the integer g. I'm actually given some decomposition of the surface into polygons. This is known as, I'm going to refer to this as a surface map. And there are two ways to think about this, which are equivalent or dual. One is that I take my abstract surface and I draw a graph on it. And I do it in a way that every region left behind when I delete the graph is homeomorphic to a disk. The other way to do it is to start with the disks, take a bunch of polygons, and glue them together along the edges. So this is similar to what Saul talked about yesterday afternoon, but without the constraints about translation or length or anything like that. These are, in some sense, abstract disks which I'm gluing together by finding homeomorphism between portions of their boundary. We're not going to, in this talk, think about things like lengths or angles or anything else. There's no geometry in this surface. It's just a combinatorial structure. Yes? Depending on context, it's more useful to think of the faces as open disks, or it's more useful to think of the faces as also including their boundary. Generally, I'm going to veer towards faces being open, But this is entirely context dependent. Pick one, fine. Yeah.
Do you allow the synthesis to be faces of the same synthesis to be glued together?
Yes, I do. I am not assuming that this is a simplicial complex, even if all of the faces have 3 edges. It's perfectly fine for there to be loops from one vertex back to itself, parallel edges which may or may not enclose faces. Everything is fair game. The only thing that I insist is that when you draw the edges on the surface, the only places that edges can intersect is at their common endpoints if they have any. Okay? So if you want more formalism, this is really more like a cellular generalization of simplicial sets than, or CW complexes than it is simplicial complexes. Now this is, I think part of the reason why I got into this is not only a convenient representation for mathematics, but this is also the standard representation for surfaces in the computer graphics and geometric modeling world. In the graphics context, you do have geometry. The faces of your surface map are quite literally flat or nearly flat Euclidean polygons in R3. But I'm not going to assume that geometry, partly because it doesn't matter for the kinds of algorithms that we're doing. So I'm no vertex coordinates, no metrics, no angles, no areas, just structure. Now, one of the things that comes with this structure is a transformation or a change of viewpoint, I think more accurately, that associates with any surface map a dual map. So the surface map has vertices, edges, and faces. There's a natural correspondence to a dual map whose vertices correspond to the faces of the original map, whose faces correspond to the vertices of the original map, and whose edges correspond to the edges of the original map. And locally, the picture looks kind of like this. Here I have an edge between 2 vertices u and v and separating 2 faces f and g. In the dual map, the corresponding edge connects the dual vertices f star and g star and separates the faces u star and v star. If u and v are the same vertex, then u star and v star are the same face, but that face meets itself. Okay? So if I have in this case, a triangulation of the surface, there's hiding underneath it a dual surface. If you're used to geometry, you can think of this as either polarity of polyhedra or Voronoi-Delaunay duality. Topologists, you know this as Poincaré duality, but it's really just a typecast. So under the hood, these things are represented by a data structure, or an abstract data type really, where simultaneously you maintain what I called previously a rotation system. Ben referred to this in the representation for enumerating knots. For every vertex, I need to record the counterclockwise order of edges incident to that vertex. And simultaneously, for every face, I need to record the clockwise order of the edges around that face. Now, these two orders are dual to each other. Around the vertex, and the dual becomes around a face. And so, at least at an abstract level, you can think of the data being stored in a combination, a sort of grid of linked lists, where in this case, the horizontal linked lists give you the order of edges around the vertices, and the vertical linked lists give you the order of edges around each face. And each edge actually shows up twice. Really, we split the edges into 2 parts, which we call darts. And then I have these blue arrows and these red arrows that point back and forth between the 2 darts. The details are not particularly important for this lecture, but this is the kind of thing that you would implement. And then if you want the data structure that corresponds to the dual map, it looks like this. I don't know if you noticed the change. See the cloud there? The names of the pointers changed. That's the only thing that changes. Okay? It's just which records you interpret as vertices and which records you interpret as faces that determines whether you're thinking about the original primal map or whether you're thinking about the dual map. The way I like to say this is duality is not a construction. Duality is changing your glasses. Okay? This data structure, by the way, like most things I like to talk about, is actually quite old. This is a snapshot from Bruckner's survey of polygons and polyhedra from 1900. This is nothing in Bruckner's survey was original. This was a 50-page, very densely written, very densely referenced survey of things that were known about the polygons and polyhedra and about elementary combinatorial topology as of 118 years ago. The representation really dates back to Hamilton studying the Icosian calculus and Kirkman and Cayley's enumeration of polyhedra and Hefter's investigations of the four-color theorem and its generalization to surfaces. But it's very old. And it goes by thousands of different names. You may have heard of half-edge data structures and winged edge data structures and doubly connected edge lists and the other doubly connected edge lists. It's all the same. Probably the single most important fact about these surface maps and what underlies the classification theorem that I referred to earlier is Euler's formula, which for planar maps says the number of vertices minus edges plus faces is equal to 2. For surfaces of genus G, the number you get at the end, the Euler characteristic, is 2 minus 2G. For some reason, Saul insisted on doubling everything when he was talking about translation surfaces. I guess because you like dividing by pi instead of dividing by 2 pi. I'm going to divide by 2 pi everywhere, so we're not going to get that factor of 2. But there's a wonderful thing about standards is there's so many to choose from. Of course, this is a long and storied history going back to Descartes, and we'll actually see a little bit of that later. But this is not just a statement that gives you a classification. There's actually an easy way to prove this, which I won't go through the details, but I'll give you the high-level structure. There's actually structural decomposition of these maps that turns out to be incredibly useful, called tree-cotree decomposition. And this is exactly, in different guise, the same structure that Dehn called a Baum-Zwiebelfigur. So take an arbitrary spanning tree of the vertices and edges of the map. It doesn't matter which spanning tree you pick. Let's call those edges red. Now, let's also consider a spanning tree of the dual graph, which I'll call C star, because it's a spanning tree of the dual graph G star, with the property that the original spanning tree T and the new dual spanning tree C star don't share any edges. Okay, so I take a largest subgraph that I can, the largest collection of edges that contains no cycles. So, or equivalently, I take the smallest subgraph that I can that touches every vertex and is connected. Okay. And so these two spanning trees in a planar graph actually eat up all of the edges. I'll come back to, in later lectures, more examples of this phenomenon. But in a surface of genus G, if you just count up how many edges there are, there are v minus 1 edges in the spanning tree. There are f minus 1 edges in the dual spanning tree, because every tree with n vertices has n minus 1 edges. And then if you do the math with Euler's formula, there are exactly 2 G edges that are left over. And so a tree-cotree decomposition for a surface map is a primal spanning tree T, a dual spanning tree C, and leftover edges L, of which there are always exactly 2G. I'll let this sink in. We're going to be using this over and over and over. This is probably the single most important, for algorithmic purposes, the single most important structural result about surface maps.
Did you say the notation? Oh, it's not C minus C comma?
Sorry, that's an M dash. That probably should have been a colon or something, you know, or a different line.
So how can we always guarantee that such T and C are always existing?
So that's a theorem of Biggs from 1971. You can choose the tree arbitrarily, and there will always be something left over for there to be a spanning tree. Another way you can think of it is the spanning cotree. You shatter the surface map into its faces, and then you reconnect them just enough to make the whole thing hang together into a single connected piece. And now there are a couple of other ways to think about it, which I think maybe I'll come back to this again later in the talk. But for now, maybe take it on faith that these things always exist, and there's an incredible amount of flexibility for how you construct them. Yes? Yes. So C star is a spanning tree of the dual graph. Those are the edges in the dual corresponding to the subset C of the edges of my original map. So T, L, and C are subsets of the original primal edge. Now, if you go to the dual map, C dualizes to a spanning tree, T dualizes to a cotree, and L dualizes to 2G leftover edges. So again, because if you just put your glasses on upside down and swap vertices and edges, you're also swapping tree and cotree. So again, it's just a point of view whether you want to think of T as a spanning tree or whether you want to think of C as a spanning tree.
Given T, C, and L, is the surface representation always unique?
Given T, C, and L, okay. The question is the surface representation always unique? So if I just give you an abstract graph and I give you these two abstract spanning trees, it's a little weird because without the rotation system, the dual graph is not defined. Right? It's really the dual map. I need to have faces in order to define the dual structure. And then once you have the dual structure, the surface map is the decomposition is completely specified. Okay, thank you for these questions, by the way. Keep them up. All right, the other piece of this puzzle is, okay, for some reason my movie isn't playing, is homotopy. Homotopy is a formalization of continuous deformation. Yes. Okay, so for non-orientable surfaces, you have to modify what a rotation system is slightly with some additional information. So remember, a rotation system, you specify the counterclockwise order of edges around each vertex. But there is no global notion of counterclockwise. So every vertex chooses its own local version of counterclockwise. And then when you go across an edge, you have to record for that edge whether the two vertices on either side are consistent or inconsistent with respect to that order. So this is called a signed rotation system. There's some other equivalent representations that are a bit more convenient but, in practice, but that's enough hopefully to convince you that you can do things. Okay, so homotopy is continuous deformation. I apologize, maybe at some future point I'll have a movie I can show you here. There we go. Homotopy. Okay, so this is somebody's implementation of curve shortening flow. So I want to continuously move a curve, in this case in the plane, but more generally on a surface. Okay? You can think of this as a continuous two-parameter map where one parameter is time and the other parameter maps the circle into the surface. Okay, so Erin referred to this earlier during her talk when she was talking about similarity of curves. Okay, so in this case, I'm doing this on a surface, so I need to be able to go back and forth between various curves, and if I can do this continuous deformation, I say that the two curves I started and ended with are in the same homotopy class, or they're homotopic. It's not hard to see that this defines an equivalence relation in the equivalence classes. Yes?
We assume that the endpoints are fixed.
Okay, if we're dealing with paths, then we assume for defining homotopy that the endpoints are fixed. If we're dealing with closed curves, typically we imagine that there's no fixed point that we want to maintain. I'll try to be clear when I want to fix a base point or not. Right? Generally, when I'm talking about closed curves, I don't want to fix a base point. So the problem is, if I'm given two paths or cycles, open, maps from an interval or maps from a circle, I want to know whether one can be continuously deformed into the other. So the two green cycles on the left are homotopic, because you can imagine sliding one around to the other, or you want to imagine Erin's picture of having a ring around the hand and a ring around the finger. You can sort of continuously deform, not necessarily as nicely as this, but you can do it. Whereas the two cycles on the left, in red and blue, there's no way to transform one into the other, and there's no way to deform the red cycle into the green or the blue cycle into the green, because other parts of the surface get in the way. And the algorithmic question is, how do you tell? Right? It's sort of clear from the picture that those two over there are homotopic, and those two are not, because one of them encloses a disk and the other one doesn't even separate the surface into two pieces. But how do you prove algorithmically that the blue and green aren't in the same equivalence class? And then there's a simpler version of this, which is just, let's ask whether a curve is contractible. This just means that it's in the same homotopy class as a curve that it's constant, it just sits at a single point. So from the picture, hopefully it's intuitive at least, that the curve on the right in red is contractible. I can shrink it down to the right end of the surface, whereas the other two are not. The green cycle is kind of hooked around one of the holes, and there's no way I can continuously deform it to make it fall off. The blue cycle, because the cycle has to stay in the surface, I can't close it up. It would be contractible if this thing were sitting in R3 and I could pull the rubber band off the surface into space and contract it. But because I have to stay on the surface, the two holes kind of keep the cycle open. Now, I'm going to refer back again to my old friend Max Dehn. Dehn studied this problem in a paper called The Transformation of Curves on Two-Sided Surfaces. And he posed the question more or less in exactly the same terms that, that I've just done, whether one can be transformed into the other by continuous deformation. But this was not the first paper or the first person to consider this problem. It was already well known through earlier works by Schwartz and Poincaré that there was sort of an in principle characterization of when two curves are homotopic, which in the next sentence he spells out the solution for surfaces with positive genus or genus greater than 1 with the help of polygon groups, what we now know as the fundamental group. And accordingly, based on the metric of the hyperbolic plane, is obvious. Let this be a lesson. Don't use that word. So, as I said, ancient history, Schwartz, I think, was the... Oh, I'm sorry.
Isn't he right?
He's...
Every time you cross an edge, you multiply by that matrix, and you reduce it to the word column in a matrix group, which is...
Right. I will remind you that you're a tenured professor in mathematics at Warwick. What's obvious for you is maybe not obvious for the rest of us.
So Jim Cannon addresses this issue in his paper.
Yeah, and the moment you cite something, that's evidence that it's not obvious.
No, he writes a paper in the 80s where he's talking about hyperbolic groups, and he said, like, I'm going to review what hyperbolic geometry is, but in Max Dehn's time this would not have been necessary because everyone knew hyperbolic geometry.
Right, so everyone knows hyperbolic geometry at this point, unlike now, at that point. It's actually the polygon groups, notice it's in scare quotes. And you know, it's actually in scare quotes in the original polygon that would have been less obvious. Okay. So I think, yeah, I'll eventually define this phrase if you haven't seen it before. But there's a characterization via a standard topological construction called covering space that goes back to unpublished notes by Schwartz in the 1870s and was spelled out in more detail in Poincaré's Analysis Cetus series of papers. This one, in, I believe it was the 5th supplement in 1905. Prior to the algorithm that I'm going to describe here, Max Dehn himself described in detail how to actually solve this problem using explicitly continuous hyperbolic geometry. But I think, you know, the more interesting version of Dehn's algorithm is the one I'm actually going to talk about, where he reduces the problem to pure symbol manipulation, to something that can be implemented in Python on your laptop in a matter of hours, provided you have the right data structures already implemented. This is was a really quite influential piece of work. It ultimately led to a bunch of different things. I'm referring here to the whole idea of small cancellation theory that underlies most of geometric group theory, or a lot of geometric group theory. You can also see, you know, versions of this as a, you can see this as one of the predecessors of automatic groups. You can see this as one of the predecessors of Gromov's discrete hyperbolicity, cat zero spaces, and so on. But for me, it's, let's take this geometric problem and turn it into an algorithm in the traditional sense that wouldn't exist until 50 years after Dehn. Okay. I'll explain this in a bit more detail, but the punchline is that given any fixed surface map, the running, if I fix the surface map and I say that's hard-coded into my Python program, and the only input is the path, which I'm going to specify as a walk in the graph, then Dehn's algorithm can be implemented to run in linear time. The running time of the algorithm is proportional to the size of the input, the description of the path as a sequence of vertices and edges. When I say given a surface, I mean given a surface map. And I'm going to say n is the total complexity of that map, vertices, edges, and faces. And g is the genus of that map. And when I say given a curve, I mean I'm given either an open walk, as in the picture, or a closed walk, as in the text. I apologize, they're inconsistent. A sequence of vertices and edges in the one skeleton of the surface map. And ultimately, I want to analyze the algorithm, present and analyze the algorithm in terms of all three parameters, n, g, and l. Yes?
Dehn's is linear in L, not in N?
If you fix n and g, if you fix n and g, it's linear in L. Actually, if you fix g and use a particular surface map, that's what Dehn actually does. Okay, so let's see what Dehn actually does. So Dehn starts by saying, you know what, I need a way to describe closed curves. Dehn didn't have surface maps, right? He just had surfaces. But he said, I need a way to describe an arbitrary curve floating around on an arbitrary surface. And so I need to impose some combinatorial structure onto my surface so that I have the tools to talk about what I'm doing. And the structure that he used, and he was not the first to use this, is what I will call a system of loops. This is a surface map that has exactly one vertex and exactly one face. By Euler's formula, it has exactly 2G edges. The spanning tree is that dot in the middle. It has one vertex and no edges. The spanning cotree is the face with no edges. And so I only have the leftover edges here. I think it was Jordan in the 1860s, actually, I believe he was still a student, who actually laid down the formal proof that any cycle on the surface can be deformed so that it lives on this graph. It's a concatenation of loops in the system of loops. Okay? So Dehn takes this as written and says, let me just assume that this is the representation that I'm given. I'm going to represent surfaces by saying I have a surface with a system of loops, and my curve is given as a walk in this graph. Okay? Now, if I want to actually build a system of loops, if I want to take the general given a surface map problem, and I want to turn it into the form where I can use Dehn's algorithm, I can do that fairly easily. So this is, if you've had a topology class where you talk about fundamental groups, you might actually remember half of this construction. Take a spanning tree of the graph and contract it down to a point. Take the dual tree. Now, when I take the spanning tree and I contract it down to a point, I now have a surface map with only one vertex, but lots and lots and lots and lots and lots of edges. So now when I delete the edges that separate distinct faces, what I'm doing is I'm deleting the edges in my cotree. Right? So starting with the surface map, I can just look at every edge and say, well, if this connects two distinct vertices, contract it. If this separates two distinct faces, delete it. If it does both, I have a choice. It doesn't matter which one I pick. And at the end, when eventually, I see loops like this where the face on both sides of the loop is the same face and the endpoints on both ends of the loop are the same vertex. I can't touch that. I can't delete it. I can't contract it. At the end, what happens is I have exactly 2G edges left, and they're the system of loops exactly in the form that Dehn wants. But that's not the only thing that I need to reduce. So if I'm given a walk in an arbitrary surface map, I need to be able to sort of deform that walk as I'm going to get a walk in this simplified map. So to do that, I'm going to imagine cutting the surface open along those loops into what's typically referred to as a fundamental polygon. Again, I will remind you that you saw this picture or something very much like it in Saul's talk yesterday afternoon, although I'm using a somewhat different identification of the edges than Saul did. Okay, so this is the octagon that you get when you cut this surface of genus 2 along these loops. And the labels just tell you how to identify the edges. So after you contract the spanning tree, and those loops are there in the reduced single vertex surface map. So if I cut along the generating system of loops, I get a picture that looks like this. There's the loops that I cut along, but then there are all of the other extra edges that are dual to the dual spanning tree. Right? And when I'm taking a walk through the original map, when I contract an edge, I just contracted in the walk as well. It just means that the walk suddenly got shorter. But when I want to delete an edge to go from have this octagon with all this internal structure to I just have a bare octagon, I need to modify the walk So that instead of traversing an edge that isn't going to be part of my system of loops, I divert the edge around the boundary of the polygon. So this red edge here will get diverted to this green path over there. And it's hopefully clear that this is something that can be executed as a continuous deformation. It's a homotopy. And so if something was contractible before, it's still going to be contractible. If two things were homotopic before, they're still going to be homotopic after all this reduction. Okay? So this is how to go from any surface map to exactly the condition that Dehn wants. The one disadvantage of this reduction is that when I contract edges, that makes the length of the walk go down. But when I delete edges and I do this replacement, the total number of edges on this polygon is 4G. And so if I always route along the shorter of the two ways around the boundary, I'm replacing a single edge with at most 2G edges. So the length of my loop gets blown up by a factor of 2G. This factor of G is going to follow us around for the rest of the algorithm. Okay? But for now, I'm just going to refer to the length of the reduced cycle as L prime. Okay? I need to stop and make sure there are no questions. Everybody kind of see what's going on? Okay. Now, I referred to this earlier about the universal cover. This is the other reason why the system of loops, why Dehn chose this, why this idea of opening the surface up into a polygon is so useful, because this construction, opening it up into a polygon, was already the basis for thinking about the universal cover of the space. So the universal cover, I won't give you the formal definition, but the intuition is you take your surface and you cut it open along the system of loops into a polygon, and then you tile the plane with copies of that fundamental polygon, so that the structure you see at any vertex of the tiling exactly mirrors the structure you see at the vertex of the system of loops. So for a torus, you're always going to cut along the two loops into a square, or a quadrilateral, but let's make it a square for convenience. And then you tile the Euclidean plane with that square, giving you a nice integer lattice. For the higher genus surfaces, you don't get a tiling of the Euclidean plane, you get a tiling of the hyperbolic plane. So again, given this surface and that system of loops, you cut it open into an octagon. But notice that at that vertex, you have 8 corners of the octagon meeting at a single point. So when you create the universal cover, or define the universal cover, you get a tiling of the hyperbolic plane by octagons where every vertex is the meeting point of 8 octagons. Okay? Now, okay, so I want to, let's just start with an infinite pile of pieces of paper shaped like these octagons. Pick up 2, and now I notice I have an edge over there labeled A on one, and I have an edge over there labeled A on another. So I glue these 2 copies together in a way that the arrows match up. And then I do this again, and I do this again, and I do this again. The only thing I need to watch out for is that at the vertex, I'm going to create a cycle of 8 octagons that close up around that vertex in exactly the pattern that you see. I mean, I haven't labeled the loops up there. That might have made the picture a little bit clearer. But for example, this octagon down here is, has its top edge labeled B, and then I go over, there's an edge labeled A, it's glued to that, then I go, there's an edge labeled B, I go just around in a circle. Right. From the point of view of the data structures, this is all defined implicitly. At no point does Dehn's algorithm actually construct this infinite object. It's all reasoned about symbolically. Okay? But it's useful for thinking about how the algorithm, why the algorithm works. For example, it was known already in Dehn's time that, okay, so any point on the surface is a point in some octagon, and I make an infinite number of copies of that octagon, which means each point on the surface lifts to an infinite lattice of images, pre-images of those points. Or another way of saying it is there are an infinite number of points up into the universal cover that project down onto the same point on the surface. Similarly, any path, or let's just stick to paths for the moment, any path on the surface lifts to an infinite number of translations of the same path up in the universal cover. And in some sense, what you can do is, say for this blue path that starts and ends at the base point, I pick an arbitrary lift of the base point, and then the blue edge says, I'm following edge C, and I go the universal cover, and one of the edges is labeled C, and I follow that edge. Okay? Now, there are an infinite number of ways to make the first choice, but beyond that, everything is completely determined. And then, as I said, it was already known in Dehn's time that a loop is contractible. A loop is a path that starts and ends at the same point in this system, if and only if it lifts to a loop in the universal cover. Okay? So the blue thing isn't contractible, but the green thing is. And the intuition is, if there's a way of continuously deforming the loop down to a point on the surface, I can take that continuous deformation and mirror it with any lift of the curve upstairs in the universal cover. Because I can shrink that green thing down to a disk up in the universal cover, I can just project that homotopy back down to the surface. I can't do that to the blue thing because, well, that blue curve isn't homotopic with its base points fixed to a point. Okay? So this gives a characterization of contractibility in terms of this covering map. Again, Dehn's 1911 algorithm actually reasons about this hyperbolic tiling by imposing the standard hyperbolic plane metric on it, and then saying, well, given whatever my loop is, I'm going to project it upstairs and then just compute the shortest path between those 2 points. And that's unique and well-defined, and it's either a single point or it isn't. But actually, you know, doing computation with hyperbolic metrics is not exactly easy. Okay, here's another example of a contractible loop. It goes around the base point. Upstairs, it goes around one of the lifts of the base point. Okay. So how does the algorithm work? So the intuition mirrors what you would do in the sort of geometric setting. I want to compute the shortest lift I can that has the same endpoints as the one I'm given. So for cycles, I want to find the shortest cycle on the surface that's homotopic to the one I'm given. And either it's going to be a single point, and then I know that the cycle is contractible, or it isn't, in which case I know that it isn't. And the algorithm is going to work in a way that intuitively mirrors what you would imagine maybe would work finding shortest paths, a shortest path in the plane. I give some wiggly path here from me to the door. Any place where there's curvature, I just locally straighten it. And that makes the path shorter because the shortest path between any 2 points is a straight line. So I'm going to mirror that local shortening in the algorithm. And because of the hyperbolic structure of this universal cover, I'm guaranteed that there are no local minima. I'm not going to get stuck in a path that I can't locally shorten, but is still not the globally shortest path. Now, these things that I'm claiming here, these are not things that should be obvious. These are outcomes of Dehn's algorithm, not feeding in, but just to guide the intuition as we keep going. Yes?
But, I mean, it's reducing of alpha. I mean, do you explicitly have a, I mean, because you went from this universal cover with you went from your translation to a universal cover which has a standard metric. So, I mean,
No, it doesn't have a metric. There's no metric. I'm not doing metrics. There are no lengths, there are no angles, there's no area, there's just structure. When I say shortening here, I mean reducing the number of edges. Reducing the description length of alpha. I'm not reducing a metric at all. Now, Dehn's 1911 algorithm, he says, let's impose a hyperbolic metric and reduce that. But that was more as a continuous process, not as a discrete symbolic process. Okay. So, what is the real key point here? Now, when I take my cycle on my surface and I want to know whether it's contractible, remember the cycle is a walk in the system of loops. That's going to lift to a walk in this infinite hyperbolic tiling. And I want to know whether that walk closes up, whether it starts and ends at the same point when I'm upstairs. So I'm going to show a very, very important property that if that loop closes up, I know something structurally about it. So to keep things simple, let me imagine for the moment that the loop, when I lift it upstairs, is actually a simple closed curve. Of course, it's not always going to be simple, but this is the key special case that drives the correctness of the algorithm. And Dehn showed that if I have a closed curve up in the universal cover, it has one of three structures. One, it's empty. It's just a single point and you don't go anywhere. Two, it has a spur. It goes along an edge and immediately turns around and comes back. Again, I'll refer back to Aaron's talk about homotopic, discrete homotopies. That actually goes back all the way to Dehn. The third is that somewhere this closed curve contains almost the entire boundary of a tile. So remember, these tiles are polygons with 4G edges. So Dehn's lemma says that somewhere there's a tile where 4G minus 2 consecutive edges show up in my lifted walk. Okay? This is where I'm using the fact that it's very important. G has to be bigger than 1. When G is 1, this doesn't work, and so I have to say that's a separate thing, don't worry about it. There's other ways to do it that are actually quite easy, but let me not talk about it. But what this means is that if I have a walk in my hyperbolic tiling that's actually closed, if it has any edges at all, then it either has a spike, which I can remove and make the curve shorter, or it has most of a tile on its boundary, which I can move across and make the curve shorter. So I can locally shorten the curve. And because this is true of every non-trivial closed curve, I can start, just by local shortening, I can reduce any closed walk in this hyperbolic tiling to a single point. And this is exactly what Dehn's algorithm does. Okay. So how do we prove Dehn's lemma? Well, as usual, I need to back up 300 years to what is now somewhat mistakenly referred to as Euler's formula, which was first described in some unpublished notes by Descartes, which were lost in a shipwreck in the Seine when Descartes died because he went to Sweden to teach geometry to the royal princess and caught a cold and didn't listen to the doctors there and instead used his own doctor from Paris who was an idiot. The ship sank in the Seine. They rescued most of his papers. They dried it out by hanging it on laundry lines on the bank. It went into a box where it was unfiled for many, many years until Leibniz, who was accused by Newton of stealing everything he did from Descartes by some people you might have heard of in England, before calculus, decided to defend himself. He would become the world's best Cartesian scholar. And so he went to Paris and he dug through every single scrap of paper in the closet, and he discovered this particular manuscript, and he took copious notes, at which point the original manuscript was lost, but fortunately somebody went through Leibniz's notes. And so we are aware of this lovely little thing where Descartes states Euler's formula. But he states it in a way that's much more similar to what Saul referred to as the Gauss-Bonnet theorem, which of course is not due to either Gauss or Bonnet, because right here it's due to Descartes, which is if I look at the number of solid angles in a convex polyhedron, the total of all the face angles is 4 times the number of vertices minus 8 measured in right angles. Okay. This is another way of saying this is if you look at the angle defect, the sum of the angles around any vertex minus 2 pi, that adds up to 8 right angles. And then he goes on further, and the second sentence in red, the total number of plane angles is twice the number of plane angles minus, or twice the number of vertices. I think one of those is faces. This is equivalent to Euler's formula in its usual statement. Okay, so this angle defect has been radically generalized to what we now refer to as the combinatorial Gauss-Bonnet theorem. Okay, this is this is Euler's formula in a fancy suit. The proof is literally just rearrange things, but it's a useful way of packaging Euler's formula that helps you derive interesting things. So what I'm going to do is assign to every corner in my surface map a number, which I'll think of as the external angle. The number doesn't have to be positive. It doesn't even have to be real. You can use complex numbers if you want. I don't know of any instance where anybody does. But I just define a number called the exterior angle to every corner, every wedge between 2 successive vertices around a vertex. And then I define in a discrete way curvature at a vertex and curvature at a face. The curvature at a vertex is this weird sum. The last term is the total exterior angle of all the corners incident to that vertex. In the middle here, I've halved the number of edges incident to the vertex. And this actually applies even if the surface has boundaries. So you may have fewer corners incident to the vertex because it's a boundary vertex than you have edges. And I should also mention this is curvature measured in units of circles. Right? So the curvature of a face is 1 minus the sum of the exterior angles. The intuition, at least for face curvature, is if you take a standard Euclidean polygon, the sum of the exterior angles is its rotation number, which is 1. And so for a flat polygon with no curvature, this kappa actually comes out to be 0. If I'm in the hyperbolic plane, the vertices get more pointy, which means the exterior angles go up, which means the curvature goes down. You get something negative. And if you're on a sphere, the interior angles get fatter, which means the exterior angles get skinnier, which means the sum goes down, and therefore the curvature goes up. You have positive curvature. And the formula says, if you define curvature this way by these formulas, then the sum of all these discrete curvatures is exactly the Euler characteristic of the surface, V minus E plus F. So how do we apply that to Dehn's lemma? So if I really have a simple closed curve upstairs in my universal cover, the interior is a union of octagons in the tiling. I'm going to label certain vertices on the boundary of this region. I'm going to call them convex. And the condition is that it's incident to exactly one corner that's in the interior of this disk. These are all the points that are marked in red. Now, if I walk through the definition of curvature, And to every corner, I'm going to assign the exterior angle 1/4. In other words, I'm going to assume every angle that you see up here is a right angle, okay? Which is not the angle that you would get from the regular hyperbolic tiling. Okay? Then what happens? The formula actually says there's a 1/4 unit of curvature at every one of these convex vertices. At every vertex that's not a convex vertex, either it's on the boundary or it's in the interior, which none of these are in the interior, but it could be in general. Every vertex that's not convex turns out to have negative curvature value.
I'm sorry, if you give 1/4 at every corner, what do you do with the faces, or maybe just say?
Faces have corners.
No, I mean.
Vertices have corners. Every corner is a right angle.
Don't you have excess curvature at the vertex then?
Well, yes. That's. Remember, these are exterior angles, right? Right. So yes, in the interior vertices, I have way too much going on, so it's hyperbolic, so it's negatively curved. The faces are also negatively curved. The only positive curvature anywhere in this picture is, by this discrete definition of curvature, is at these convex vertices. There was a question over here.
Just was to point out that this looks very hyperbolic.
It is. That's right, right. So the standard hyperbolic tiling actually puts all of the curvature into the faces by having the exterior angle at the vertices be some function of g. Here, I'm spreading the curvature, some to the vertices and some to the faces, but in a way that makes the computation convenient. So these convex vertices have positive curvature. Everything else has negative curvature. But the discrete Gauss-Bonnet theorem says the sum of all the curvatures is the Euler characteristic of the disk, which is 1. It's a sphere, which has Euler characteristic 2, where I've deleted one face. So V minus E plus F goes down by 1. I get an Euler curvature of 1. So the positive things, V plus, must make up all of the positive curvature, which goes into that 1. And so a little bit of arithmetic will imply that the number of convex vertices is at least 4g minus 4 times the number of faces plus 4. That means that just by an averaging argument, some face has at least 4g minus 3 convex corners. And then case analysis implies that those corners must be consecutive around the face. And that's the end of the proof. Okay? So everything is buried in this discrete Gauss-Bonnet formula, which again is just Euler's formula in disguise. Yes? Every corner in the map can be assigned a different number, but once I've assigned it, then I define curvatures and I can do the formula. In this case, I chose the same value 1/4 for every corner in the map. That's not required by Gauss-Bonnet. It just was convenient for this proof.
But that will be cancelled out in the sum, right?
That's correct. Right. So in this summation, you'll notice that the sum of the exterior angles appears positively in the vertex curvatures and negatively in the face curvatures. And so when you add the curvatures up, all those angles just vanish. Okay? So that's it. That's Dehn's algorithm. You look for a part of your loop that has most of an octagon on it, and you replace it with the rest of the octagon, and you do this over and over again, and either you end up with nothing or you don't. And if you end up with nothing, then the curve is contractible, and if you don't, then it isn't. Right? So I went a bit slower than even I expected to, but so there's a bunch of stuff that I'm going to need to skip. But if you implement this really, really, really carefully, you can get the running time down to this expression here. I need to spend some time building my tree-cotree decomposition and contracting and deleting to get my system of loops. And then because of the reduction, I increase the complexity of my curve by a factor of g. And so the reduction, which if I do it carefully, takes linear time. Linear is now g times L. This is a little bit unsettling because I don't like extra factors of g floating around. So at this point, I'm going to go into fast forward mode, let it wash over you, admire the pretty pictures, read the paper later if you're interested, ask me questions later if you're interested. But I just want to show you how to get rid of the factor of g.
Can I ask a
Yes.
question before that?
Yes.
At the beginning, you were given like a loop.
Yeah.
You were asking if it's contractible, and then you just transferred to loop in the tiling.
Yes.
And yeah, in the tiling, it's always loop. Yeah.
Right. Right. If it's contractible, then it'll be a loop upstairs as well, and that's what we're looking for.
But then you kind of have to check start and end point.
Well, so what actually happens if you're given a closed walk that's not contractible. Then what happens is you're actually shortening a path up in the universal cover whose start and end points are different. And you'll reach a point where there are still edges left, but there's not most of a tile left. And that implies that the endpoints are different. OK, so to do this in linear time, instead of going to a system of loops, I have to go to a slightly different structure, which was introduced by Lazarus and Revaux, and which Kim Whittlesey and I refined to refer to as a system of quads. This is the radial graph of the system of loops. You have two vertices instead of one, and your faces are quadrilaterals instead of being octagons. And this has the advantage that I don't inflate by a factor of g. It gives you a different regular hyperbolic structure. Instead of tiling by octagons a to the vertex, it gives you a tiling by quadrilaterals a to the vertex, with two different kinds of vertices, the one that corresponds to the original vertex of the system of loops and the other that corresponds to the original face of the system of loops. The basic structure is the same but of the algorithm. I do local curve shortening, but there are a couple of things that make this complicated. One is that I don't have the same Dehn's lemma that I had before. I don't necessarily have three edges of a quadrilateral on a closed loop in this tiling. So I have to do a little bit of extra work to make it fast, and that extra work is the modern invention known as run length encoding. So instead of encoding the path by the labels of the edges, I'm going to label it by what we call a turn sequence. When you walk into a vertex, how many steps do you turn left or turn right? So I get a number between plus g and minus g. And then if I see the same turn number appear multiple times, I'm going to just record, I see 4 2s instead of 2, 2, 2, 2. And then from now on, I only do run length encoded things. And the reason I want to do run length encoding is the analog of Dehn's lemma is what we call the bracket lemma. I think it first showed up in the literature in the work of Gersten and Short, although it's implicit in lots of other earlier things. These are patterns that look like this in the path where things could be locally shortened. You have a spur here, or you have a left bracket or a right bracket. These show up as particular patterns in the run length encoding. And the lemma says there are always brackets or spurs in any closed loop in this tiling by quadrilaterals. The proof is, again, a case analysis using the discrete Gauss-Bonnet theorem. You label vertices. You say all the positive stuff has to be here, and the overall curvature has to be 1. So there must be enough positive curvature to make that up, and enough more positive than negative. And so you, in fact, always find at least 4 brackets somewhere on your closed curve. Doing the reduction involves simple manipulation of the run length encoding. So getting rid of a standard left bracket, right bracket, or a spur. You manipulate the turns according to these simple patterns. And then there are some additional special cases that show up when the curve is so short that the bracket wraps all the way around. But then ultimately, you just have an algorithm that looks like this. You start with your run length encoded turn sequence. You look at a window of 5 runs, and either it contains a spur or a bracket, in which case you do the magic to it and back up a few steps. Or you say it doesn't have a spur or bracket, and you just go to the next, you slide the window forward. If you just walk through the analysis carefully, even without doing the things that you would need to do to actually make Dehn's original algorithm run in linear time, you get something that runs in linear time. There's a bit more to do with if you want to tell whether two things are freely homotopic, mostly involving multiple cases, again with Gauss-Bonnet. Okay, this is the part I planned to skip, so I'll just skip it. And I want to finish briefly, very briefly, talking about higher dimensions. And mostly I'm using this as an advertisement for other people who are in the room. Okay? So you could ask, okay, great, we know how to tell whether two cycles on a surface are homotopic, essentially by leveraging this discrete symbolic avatar of hyperbolic geometry. What can we do with higher dimensional things? If I've given a cycle in a higher dimensional space, can I decide whether it's homotopic or not? And Joel referred to this yesterday, that there's this huge sequence of undecidability results. Joel referred to the homeomorphism problem, but there's similarly another version of this result for homotopy. So Dehn actually formulated the contractibility question as he reduced it to, well, I have this description of a group, and I have a string that represents an element of the group. Is this the trivial element of the group? And similarly, the homotopy question is what's called the conjugacy problem. I've given two words in the group, and I want to know basically whether I can get from one to the other by applying a commutator. Unfortunately, what Dehn did when he did this reduction is he reduced a solvable problem to an unsolvable problem. And Dehn actually points out in his paper, when he does this, he actually does the reduction in full generality, and then he says, we figured out how to do this for surfaces, but for more complicated spaces, this seems to be as hard as any other problem in mathematics, end quote. Turing came 25 years later and actually proved him right, and actually proved that it was undecidable. And this is, Joel referred to this in a seminal work by Novikov and Boone, building on earlier work by Turing and many others. And then there's this construction by Markov that Joel showed us a version of for the 5-sphere, but there's a somewhat simpler construction that shows, given any finite represented group, you can create a 2-dimensional cell complex or a 4-manifold that has exactly that group as its fundamental group. I think this is actually Seifert and Threlfall, not Markov, but Markov was the one who pointed out the connection. So once you get up to anything more complicated than surfaces in 2D, things get ugly. Once you get up to manifolds in anything up to 4D, things get ugly. So there's this gap. What about 3? Well, it turns out that it is decidable whether a curve in a closed curve in a 3-manifold is contractible. But we needed Perelman to prove the Poincaré conjecture to know that. Thanks to Perelman, we now essentially have a classification of 3 manifolds. We know the kinds of geometric structures that can show up. And for each of the geometric structures, there's a different algorithm. If you put the pieces together, I pulled this out of one of Erickson and Duverger's papers, you get a kind of a brute force algorithm that tries all of the triply exponentially many ways of contracting given the right correctly structured cellular decomposition of the manifold. But This is not really explicit anywhere, and the triply exponential time is without really trying to optimize anything at all. There have been a couple of very recent results, relatively recent results, that solved some special cases in where we know a little bit more about the complexity. One of these, which Joel, I think, will tell us about later this week, if not this afternoon, is if I have a simple boundary curve, a simple curve on the boundary of a three-manifold. For example, if I have a knot sitting in R3, and I take a tubular neighborhood S3, and take the tubular neighborhood of the knot, the complement is the three-manifold, and the knot itself is the simple boundary curve. There is a non-deterministic polynomial time algorithm to decide whether such a curve is contractible. Or in other words, there is a proof. I can prove to you that such a curve is contractible in a form that you can check in polynomial time. And it immediately follows that there's an exponential time algorithm to create that proof. But it's not known whether I can construct that proof in polynomial time. And this is all based on normal surface theory, which Joel will tell us quite a bit about. And then there's a more recent result by Erickson de Vergier and his colleague Parsa, whose first name I forget, I apologize, that if you don't insist on the curve being simple, but you do insist on the curve being on the boundary of your manifold so it can self-intersect, then we don't necessarily know that this more general problem is in NP, but we do know that it can be solved in exponential time. The part, if I understand the result correctly, that is uncertain is the exponential dependence on the number of self-intersection points. And the way the algorithm proceeds is essentially you resolve the self-intersection points in all possible ways, and then you reduce to the previous problem. So we loop back to the Gauss code problem again, because we can't get away from it. As far as I know, nothing similar is known about testing the contractibility of closed curves that lie in the interior of a three-manifold, or maybe the three-manifold doesn't have boundary. This seems to be an open question whether there is even a singly exponential time algorithm, or whether there's an exponentially long certificate, if it is contractible, that you can check. So it would put it in non-deterministic exponential time. I think even that would be an advancement on the state of the art. But it's decidable, so some people are happy, but not me. I think that is all I want to say. So I'm happy to take more questions, but thank you for listening. Joel, sorry, Saul.
Well, so a stupid request, not question is, do you want to just zip through the slides that you skipped so we can let them wash over us again?
Okay, so you haven't had enough fire hose, so I'll point the fire hose at you a little bit more. So let me suppose now that the edges in my surface map have lengths. And now I don't just want to know whether something is contractible or not. I want the shortest curve in the same homotopy class. Now, the previous things handle the case where the surface map is a system of loops or a system of quads, and all the edges have weight 1. Now I'm assuming arbitrary weights. I'm not even assuming the triangle inequality, just that every weight is a non-negative number. So the way that Eric and I solved this problem was, first, we showed that you can pull out a substructure similar to tree-cotree decomposition that decomposes the map into what we call a tight hexagonal decomposition. So in blue, you might recognize a pants decomposition. Good, if you've seen those things. And the red kind of cuts each pair of pants into 2 hexagons, but with exactly this combinatorial structure. Okay? This is actually by far the trickiest part of the paper, is actually making this work. So we can essentially find a way of decomposing the surface by these cycles, each of which is as short as possible in its own homotopy class, but we don't know what those homotopy classes are in advance. Once you have this, this gives you, again, a very crude hyperbolic structure. Okay? Now, inside each of these hexagons, there's a complicated planar map. There's mountains and valleys and ridges and what there's curves. Again, it's more or less an arbitrary weighted planar graph going on inside each of those hexagons. But for now, let's just forget all that and look at the crude structure, which you might recognize. This crude structure has the property that the tiling looks like a bunch of hyperbolic lines. And so if I temporarily impose a hyperbolic metric, they really are hyperbolic lines. And the nice thing about hyperbolic lines is the shortest path can only cross one of these lines once. What we do is we take in our original curve, and then somehow we need to figure out which lines this curve crosses once, because those are the lines that separate the start of the path from the end of the path. That we can do using small cancellation, using a variant of Dehn's algorithm again. Okay? Once we do that, we have the collection of lines that it crosses. We construct the union of the tiles that could contain the path. This green region is everywhere I can get to by crossing those highlighted lines once and not crossing any other line. Again, using Gauss-Bonnet, one can show that the number of tiles that you need to put together is not that big. And then once we do this, we now open up the black box and we glue in the appropriate planar graphs into each of these pieces, run Dijkstra's algorithm, and we're done. Let it wash over you. Stare at the pretty pictures. Read the paper if you're interested. Yes?
What's the abstraction for studying the contraction of curves in hyperbolic three manifolds? Do you have the exact same? You can pave your hyperbolic space.
So in hyperbolic three manifolds, you're right. Everything is much easier. The problem, of course, is that not all three manifolds are hyperbolic. Yes, but the problem is that most is not all, right? So for the hyperbolic case, sure, you can do local curve shortening and everything is fine and wonderful, but if you're given a non-hyperbolic knot, or a knot that you don't know whether it's hyperbolic, or you want to know whether two non-hyperbolic things are the same, things get ugly. But fortunately, thanks to Joel and others, not too ugly. Mm-hmm.
I was wondering what kind of data structure are we talking about here? It's the same concept about tree-cotree decomposition still applicable?
Okay, so the question is, what data structures do we use when we're thinking about three manifolds? And I'll refer back to Ben's talk yesterday. The industry standard here is to use a simplicial complex, or perhaps more generally a delta complex or a simplicial set. So you will have a simplicial complex, but you might allow simplices to glue together in non-standard ways. There is a notion of tree-cotree decomposition, is sometimes referred to as the spine of a complex. I'm not the right person to ask about exactly how that's used or exactly what the similarity is. In principle, you can define something, but the dimension counts don't quite work. So just a tree in the primal and the tree in the dual is not going to be enough. There's going to be all this two-dimensional stuff in the middle that is more or less everything, that the dimension counts don't quite work. But there are similar structures which I'm not well informed enough to intelligently talk about, so I'll shut up. Yes? Yes, for non-orientable surfaces, it actually, For many of these problems, the simplest thing to do is just create the orientable double cover. So you cut the surface open and you take 2 copies of the polygon, glue it together, and that gives you an orientable surface with twice the Euler characteristic. And then you just lift everything to that and run the other algorithm. In fact, all of the stuff that I've done here with Dehn's algorithm, as long as the Euler characteristic is negative, doesn't care whether the surface is orientable. The proofs go through without any change. It's just there's some differences in the quantities involved, which I didn't want to worry about. So in this case, really everything goes through. For the shortest homotopic paths, we had to lift to the oriented double cover. We needed orientability for the algorithm to work. But then once you do that lift, you get an extra factor of 2 in a few places, but that's it. Yes?
What about homotopy of spheres in 3 manifolds?
Excellent question. I have no idea.
What was the question?
Homotopy of spheres in 3 manifolds. So instead of asking, Ben, you talked about essential tori, right? Okay, given a torus, how quickly can you tell if it's essential? Okay, I don't know.
I think the answer is doubly exponential time in the theory.
Right, okay, so there. Maybe we can do better, I don't know. Maybe, is there some thought that maybe that might be in NP rather than doubly exponential?
Part of the question is are you measuring sorry, I can't attend the slide, but are you measuring the bit length with the torus or just the...
Let's say you're given a simplicial complex for a 3 manifold, you're given the normal coordinates of a torus, which you can verify it's connected and you can verify its Euler characteristic quickly.
Probably part of the answer is that...
Yeah.
That's harder, right? I mean, you weren't using normal curves. You were using cut sequences.
Okay, so...
We should be given the same.
Okay, so you want to be given the explicit thing. Okay, so that increases the length of the input, which means as a function of the input, the running time just went down.
That's right.
Okay, so we made the problem easier by making the input representation more explicit. Fine. Okay, so given
That's NP now.
that's in NP now, deciding whether it's.
Sorry for the torus. The embedded torus, like living in the 2 skeletons, is essential. That should be NP.
That should be in. Okay. So Saul says if I'm given something in the 2 skeleton that's a torus explicitly, then there's a non-deterministic polynomial time algorithm to decide if it's essential.
Oh, you want to prove it's essential, not to prove that it's exponential time.
Okay. So it's complicated, and I'll let Ben and Saul and Joel argue about what the actual state of the art is, because I clearly don't know.
We have a last question here.
Yes?
Just check. So, is it right that in the ideal world where I have a real RAM machine, I could avoid Dehn's algorithm, I could just lift everything to hyperbolic tiling and check the
Okay, so this is an interesting question. So in the real world, I have actual computers that can do math. I'm repeating the question. In the real world, we have real computers that can do real math. Can we avoid all this symbol manipulation by just lifting literally directly to the hyperbolic plane and doing hyperbolic geometry? You could, but that's actually harder. Right? Notice the algorithm that I actually did here, the only math I need to do is I need to keep track of a bunch of labels and look for patterns in strings. If you want to actually do hyperbolic geometry, well, then at the very least you need exact implementations of hyperbolic trigonometric functions, which don't exist. Maybe you're happy with floating point, but this is a can of worms, especially with the behavior of hyperbolic spaces. Small errors propagate very quickly, so that's really a bad idea.
That's why there's that real range.
So even on a real, so there are various flavors of real RAMs. Typically you want to assume things that it's reasonable to assume computers can do, like addition and multiplication. If you assumed a real RAM model that had hyperbolic trig built in, yeah, you could probably do something. But at this point, we've left the real world behind quite a bit. So you really don't want to do it this way.
right, let's thank Jeff again.
Okay, thank you.